Section: Introduction. In this section, we discuss the advancements in large language models, LLMs, and their impressive performance in various natural language processing tasks, such as content generation, translation, and sentiment analysis. Recently, reasoning-enhanced models like OpenAI's O1 and DeepSeek's R1 have emerged, showing notable improvements in complex reasoning, especially in mathematical and logical tasks. However, their effectiveness in the financial sector is still largely unexamined. Financial tasks require rigorous reasoning, which includes not just numerical calculations but also a solid understanding of financial terms, regulations, and economic principles. Unlike general reasoning, financial reasoning involves 1. Grasping specific terminology, 2. Establishing and manipulating relationships between financial concepts and numbers to reach accurate conclusions, and 3. Understanding the structure and content of financial tables. Therefore, evaluating LLMs' reasoning abilities in finance is essential to connect general AI reasoning with financial applications. Effective financial reasoning necessitates models that can integrate textual, numerical, and structured data, emphasizing the need for adaptations tailored to the financial domain. In our study, we aim to thoroughly assess the performance of current reasoning models and analyze their capabilities in financial tasks. We seek to provide insights into the strengths and weaknesses of these models in financial applications, guiding future research in financial AI. We focus on several key areas. 1. The transferability of general domain reasoning enhancements to financial reasoning tasks. 2. The impact of reasoning enhancements across various financial tasks. 3. The performance differences between smaller reasoning models and larger LLMs, and 4. The limitations of LLMs in handling complex financial reasoning challenges. We evaluated 16 LLMs from families like GPT, Llama, DeepSeek, and Qwen on 3 financial datasets, Finca, DM Simplong, and XBRL Math, which include financial text, tables, and equations. Our selection features both general-purpose and reasoning-enhanced models, ensuring a comprehensive assessment across different scales. These datasets are designed to evaluate various aspects of financial understanding, including numerical reasoning, table interpretation, terminology comprehension, long context processing, and equation solving. From our experiments, we found that general reasoning enhancements do not consistently improve performance in financial tasks. In fact, some models performed worse than general-purpose ones, indicating difficulties in understanding financial terminology and reasoning over complex data. We also observed that while improvements in pre-training and model size help in general domains, financial task performance tends to plateau after reaching a certain model size. The effectiveness of different reasoning strategies in financial tasks varies significantly. Techniques designed for general domains often do not translate well to financial reasoning. However, methods like tool-integrated reasoning and knowledge distilled from general models can enhance numerical accuracy in financial contexts, though their impact on terminology comprehension and multi-table reasoning is limited. Based on our findings, we developed a reasoning-enhanced language model specifically for financial tasks, using LLAMA 3.1 to 8b Instruct as the backbone due to its strong performance among smaller models. We enhanced its reasoning capabilities through fine-tuning and reinforcement learning, inspired by successful strategies from other models. Our results show that even simple fine-tuning can lead to significant performance improvements across multiple datasets, sometimes matching advanced closed-source models. In conclusion, we are the first to systematically explore the reasoning capabilities of enhanced LLMs in financial tasks, demonstrating that domain-specific enhancements lead to substantial performance gains. We also highlight the need for improved understanding of financial knowledge, better handling of multi-table reasoning, and the development of diverse enhancement strategies to boost LLM performance in financial reasoning tasks. Section Summary. In this section, we explore the performance of large language models, LLMs, in financial reasoning tasks, highlighting that general reasoning enhancements do not consistently improve outcomes in this domain. Our findings indicate that domain-specific adaptations, such as fine-tuning with financial data, significantly enhance model performance, underscoring the need for tailored approaches to effectively address the complexities of financial reasoning. Section: Methods. In this section, we outline our methods and datasets used to assess the capabilities of various reasoning-oriented and general large language models, LLMs, in financial reasoning tasks. We selected 3 distinct tasks. 1. FINQA. This is a large dataset aimed at numerical reasoning in finance, featuring expert annotated question-answer pairs. It emphasizes complex numerical reasoning that requires combining structured data, like tables, with unstructured data, such as text from financial reports. The dataset includes many financial terms, making it challenging for models to accurately understand and extract relevant information. 2. Doc Math. Simplong. This dataset serves as a benchmark for evaluating LLMs' numerical reasoning, particularly with long documents that include specialized content and tables. The Simplong subset specifically tests models on their ability to reason over lengthy financial documents with multiple complex tables, requiring them to extract pertinent information from extensive contexts. 3. XBRL Math. This dataset assesses LLMs' numerical reasoning in the context of XBRL filings, which are structured financial documents using standardized taxonomies. It includes USGAAP XBRL tags, equations, and complex numerical relationships. Models must extract and interpret interconnected financial terms and formulas, such as the formula for annual percentage rate, which involves fees, interest, principal, and loan term days. Understanding the XBRL structure and numerical dependencies is crucial for accurate financial analysis, making this dataset a key benchmark for evaluating LLMs in complex financial reasoning. We provide more details about these datasets in a table. By experimenting with these 3 datasets, we aim to evaluate the model's abilities to understand financial terminology, extract relevant data from various financial reports, and reason over long contexts and multiple tables. For our evaluation, we selected models from the GPT, Llama, DeepSeek, and Qwen families, known for their effectiveness in natural language processing tasks. Our selection includes models of various sizes, from smaller ones with 8 billion parameters to larger models with 70 billion parameters, and even larger models like DeepSeek R1, which has around 700 billion parameters. We also included advanced closed-source models like GPT-4o and GPT-01. The models we evaluated are as follows. 1. GPT-4o, OpenAI's latest model with multimodal capabilities and improved efficiency for real-time reasoning across text, images, and audio. 2. GPT-01, an optimized version of the GPT series, designed for enhanced reasoning and problem-solving. 3. GPT-03 Mini, a compact version of the O3 model, optimized for efficiency while maintaining strong language processing. 4. DeepSeek V3, a model with 671 billion parameters that activates 37 billion per token for efficient reasoning. 5. DeepSeek R1, the first-generation reasoning model from DeepSeek, performing comparably to OpenAI's O1 in various tasks. 6. Qwen 2.5-72b Instruct, an open-source model from Alibaba that excels in both Chinese and English tasks with advanced instruction tuning. 7. Qwen 2.5-72b Instruct Math, a variant fine-tuned for mathematical reasoning, achieving strong results in complex problem-solving. 8. Llama series models, a widely used open-source model family known for its accessibility and performance, trained on diverse multilingual and domain-specific data. In our experiments, we primarily focused on instruction fine-tuned versions of these models, ranging from 8 billion to 70 billion parameters. We also included DeepSeek R1 distill models, which are fine-tuned on data distilled from DeepSeek R1, balancing efficiency and performance in instruction following tasks. Section Summary. In this section, we evaluate the capabilities of various reasoning-oriented and general large language models, LLMs, using three distinct financial reasoning datasets. FINQA, which focuses on complex numerical reasoning. DocMath, Simplong, which assesses reasoning over long financial documents. And XBRL Math, which tests understanding of structured financial data in XBRL filings. We select a range of models from the GPT, Llama, DeepSeek, and Qwen families, including both small and large-scale versions, to comprehensively assess their performance in extracting and reasoning with financial information. Section: Evaluation Settings. In this section, we outline our evaluation settings. For each dataset, we present the large language models, LLMs, with a context that includes financial reports, tables, equations, and symbols, along with a specific question. Following previous research, we use a general prompt to guide the model in answering based on the provided context. The models must extract relevant information and perform calculations using the numbers and concepts from the context, which requires strong logical reasoning skills in financial scenarios. The results are usually shown in a mathematical format, but differences in how numbers are represented, like percentages and rounding, can lead to variations in the final outputs. Additionally, models focused on reasoning, such as DeepSeek R1 and GPT-01, often provide a detailed step-by-step reasoning process before reaching their final answers. Inspired by DocMath, we adopt an LLM as judge approach to assess model performance. We first use an LLM, specifically GPT 3.5 Turbo, to extract the final answer from the model's output. Then, we apply a mathematical comparison method to check if the result is correct. For larger models like DeepSeek V3 and DeepSeek R1, or closed-source models like those in the GPT series, we conduct our experiments using APIs from Together AI and OpenAI. We specifically utilize versions like GPT-01, 2024, 1217, GPT-03 Mini, the 31st of January 2025, and GPT-40, the 6th of August 2024 for our evaluations. For other models with 72 billion parameters or fewer, we generate results using the VLLM framework on 4 A100 GPUs, each with 80 gigabytes of memory, allowing a maximum generation length of 512 tokens. To better understand how enhancing reasoning in a specific domain benefits financial tasks compared to general reasoning, we developed Fino1, a reasoning-enhanced LLM tailored for financial tasks. We first create high-quality training data with specific reasoning paths based on the FINQA dataset, which includes over 5,000 open-ended question-answer pairs from financial reports and tables. This dataset combines both text and tables, presenting a moderate difficulty level, making it ideal for training reasoning-based models. For generating reasoning paths, we use GPT-40, which has shown strong performance across various datasets, achieving results similar to the best models on FINQA. Following this, we refine the reasoning paths generated by GPT-40 using Watuo GPT-01. The refinement involves a verifier that checks the correctness of the generated reasoning. If the verifier finds an issue, the model iteratively improves the reasoning path by using one of several strategies: backtracking to fix inconsistencies, exploring new reasoning routes, verifying intermediate steps, or making targeted corrections. The refinement process starts with a prompt to generate a reasoning path and an answer, which the verifier then evaluates. If the answer is incorrect, we apply one of the strategies until we arrive at a correct and logically sound answer. After preparing the reasoning data, we fine-tune Llama 3.1-8b Instruct, which we selected as the best backbone model based on the performance of 8 billion parameter models. We first use the curated dataset for supervised fine-tuning, where the question is the input, and the reasoning path along with the final answer is the output, helping the model learn structured financial reasoning. Next, we implement reinforcement learning with a reward model that assesses the quality of the generated reasoning paths. Following previous work, we use a verifier-based sparse reward mechanism and optimize the model using proximal policy optimization, PPO. The verifier checks the correctness and coherence of the reasoning path. If an error is found, the model refines the reasoning steps through backtracking, exploring alternatives, verification, and correction. This two-stage approach enhances logical consistency, depth in financial reasoning, and accuracy in solving equations, ultimately improving model performance on financial benchmarks. During the supervised fine-tuning phase, we trained the model with a learning rate of 5 × 10⁻⁻6 for 3 epochs, using a maximum sequence length of 8,192 tokens. We applied low-rank adaptation, LoRa, to efficiently update parameters, reducing computational costs while maintaining performance. In the subsequent reinforcement learning stage, we lowered the learning rate to 5 × 10⁻⁻7 and trained the model for an additional 3 epochs. The previously trained reward model was used to evaluate the quality of the model's reasoning paths, guiding optimization through proximal policy optimization, PPO, to enhance the model's ability to generate accurate and coherent financial reasoning. Section Summary. In this section, we describe our evaluation settings for LLMs in financial reasoning tasks, where models analyze financial reports and perform computations based on a structured context. We also outline our approach to enhancing domain-specific reasoning through a two-stage training process, combining supervised fine-tuning and reinforcement learning to improve logical consistency and accuracy in financial benchmarks. Section: Overall Results Analysis. In this section, we analyze the overall results of our models across 3 datasets. Our findings, summarized in a table, show that DeepSeek R1 achieves the best performance at 68.93, largely due to its strong results in XBRL math. Its distilled versions, DeepSeek R1 Distill Llama 70B and DeepSeek R1 Distill Qwen 32B, follow closely behind. Among larger models, GPT-4o performs well but falls short of DeepSeek R1 because of its lower XBRL math score. General-purpose models like Qwen 2.5-72b Instruct and Llama 3.3-70b Instruct also show strong results, with Llama 3.3-70b significantly improving over earlier versions. Interestingly, these models outperform reasoning-focused models like GPT-o1, indicating that general reasoning strategies may not be effective for financial tasks. In the 8B category, Fino1 to 8B stands out with a score of 61.03, showing strong task optimization. However, reasoning-enhanced models have mixed results. While they improve XBRL math scores, they often perform worse on Finca and DM Simplon. This suggests that different reasoning strategies yield varying benefits, highlighting the need for task-specific optimization. From our results, we draw several key insights about large language models, LLMs, in financial reasoning tasks. 1. General reasoning enhancements do not always improve financial task performance. For instance, while models like GPT-o1 and DeepSeek R1 excel in logical reasoning, they do not consistently outperform others in financial benchmarks. This indicates that financial reasoning requires a deep understanding of specific terminology and structured data, rather than just enhanced logical capabilities. 2. Different reasoning strategies yield varying improvements based on the task format. For example, GPT-o1 underperforms compared to GPT-4o in Finca and DM Simplon, suggesting its reasoning strategies are not tailored for financial logic. Similarly, Qwen 2.5-72b Instruct Math shows a boost in XBRL math but declines in other financial tasks, indicating that enhancements in mathematical reasoning do not always translate to broader financial applications. 3. Increasing model size does not guarantee better performance in financial tasks. For example, DeepSeek 70b performs similarly to its smaller variant, DeepSeek R1 Distill Qwen 32b, suggesting that in financial contexts, smaller models can compete effectively by focusing on numerical reasoning rather than complex language processing. 4. Enhancing pre-training data and strategies in general domains can also benefit financial tasks. Models like Llama 3.1 to 8b Instruct show significant performance improvements due to better datasets and training strategies, which enhance their capabilities in financial reasoning. 5. current reasoning models struggle with long financial contexts and cross-table correlations. Many financial tasks require synthesizing information from lengthy reports and structured tables, and our results indicate that LLMs face challenges in this area, particularly when integrating numerical and textual information. 6. Reasoning enhancements based on financial data improve performance across all datasets. Our model, Fino1 to 8b, which uses reasoning paths from GPT-4o, shows substantial improvements in all tasks, demonstrating the effectiveness of reasoning-driven training. Overall, our insights reveal that financial reasoning presents unique challenges that differ from general NLP and mathematical reasoning. The variability in performance across tasks emphasizes the need for specialized training methodologies and improvements in model architecture to enhance financial comprehension and reasoning capabilities. Section Summary. In this section, we analyze the performance of various models on financial reasoning tasks, finding that DeepSeek R1 outperforms others, particularly in XBRL math, while general reasoning enhancements do not consistently translate to financial task improvements. We also highlight the importance of specialized financial training, as different reasoning strategies yield varying results across tasks, and larger model sizes do not always guarantee better performance in financial contexts. Section: Error Analysis. In this section, we analyze the reasons behind the underperformance of reasoning-enhanced models like DeepSeek R1 and GPT-o1 in financial tasks compared to general-purpose models such as GPT-4o and DeepSeek v3, particularly using the Finca dataset. We focus on instances where DeepSeek R1 gives incorrect answers while DeepSeek v3 provides correct ones. We identify two main error patterns. First, DeepSeek R1 often over-reasons and fails to follow instructions closely. For example, when asked to sum values, it complicates the response by detailing the calculation instead of simply providing the total. Second, DeepSeek R1 shows a lack of financial sensitivity compared to DeepSeek v3. It misinterprets the average share price in the UK employee share purchase plan, confusing the employee purchase price with the actual compensation expense per share. This error arises from its inability to distinguish between compensation expense and fair market value, leading to an inflated figure. In contrast, DeepSeek v3 accurately identifies the compensation expense per share, demonstrating a gap in DeepSeek R1's financial reasoning skills, especially regarding accounting conventions for share-based compensation. Looking ahead, we recognize that creating effective reasoning models for financial tasks involves unique challenges. Our analysis points to three key areas for improvement. 1. We need to enhance models' understanding of financial knowledge and terminology. While reasoning-enhanced models perform well in general contexts, they often lack the specific knowledge required for financial tasks. Future efforts should focus on integrating financial documents and regulatory materials to improve their grasp of domain-specific language. 2. We should improve models' capabilities in handling multi-table reasoning and lengthy financial contexts. Our findings show that even large models struggle with long financial reports and cross-referencing multiple tables. Future strategies should aim to develop methods for logical inference among tables and enhance understanding of extended contexts. 3. We must conduct a deeper analysis of reasoning strategies in models like GPT-o1 and DeepSeek R1. Despite their advanced reasoning features, these models do not consistently perform better in financial tasks. For instance, GPT-o1's chain of thought prompting does not yield improvements in financial benchmarks, while DeepSeek R1's reinforcement learning approach enhances structured numerical reasoning but falters in text-based financial reasoning. Understanding these differences is crucial for designing reasoning strategies suited for financial tasks. To build robust financial reasoning models, we need to focus on domain adaptation and architectural improvements. Future work should prioritize specialized pre-training, techniques for multi-table comprehension, and optimization for long contexts to effectively tackle complex financial documents and reasoning challenges. Our research builds on three main areas: the development of general-purpose and reasoning-enhanced language models, the application of large language models in finance, and the study of reasoning capabilities in financial tasks. Recent advancements in large language models have shown impressive abilities in various tasks, leading to the creation of specialized models like DeepSeek R1 and GPT-o1, which utilize techniques such as chain-of-thought prompting, self-reflection, and reinforcement learning from human feedback. These models excel in mathematical reasoning and logical inference tasks. Section Summary. In this section, we analyze the underperformance of reasoning-enhanced models like DeepSeek R1 and GPT-o1 in financial tasks compared to general-purpose models, identifying key error patterns such as over-reasoning and a lack of financial sensitivity. We propose improvements in financial reasoning models, emphasizing the need for better understanding of financial terminology, enhanced multi-table reasoning capabilities, and tailored reasoning strategies to address the unique challenges of financial contexts. Section: LLMs in Financial Applications. In this section, we discuss the use of large language models, LLMs, in finance, which has become a hot topic. We see these models being tailored for various tasks, including analyzing financial texts, predicting market sentiment, and creating automated trading strategies. Recent developments have led to finance-specific models like Bloomberg GPT, Fin GPT, and PIXIU, as well as OpenFin LLMs. These models are trained on financial data to better grasp the specific language and concepts of the field. They have shown success in tasks such as analyzing financial sentiment, reviewing earnings calls, and ensuring compliance with regulations. We also address the unique challenges of financial reasoning, which involves numerical calculations, specialized knowledge, and logical thinking. Recent research has looked into how LLMs perform in financial reasoning tasks, such as interpreting financial documents, solving mathematical problems in finance, and analyzing structured data. These studies emphasize the need for both expertise in finance and strong reasoning skills. Our work builds on this research by systematically assessing how improvements in reasoning within advanced LLMs apply to financial tasks, offering insights into the effectiveness of various reasoning methods and pinpointing areas where financial reasoning can be enhanced.